Hello and welcome back. In this presentation, we will look at a few numerical examples to demonstrate how to obtain the decomposition for the unknown input. In the previous presentation, we show how to analytically obtain the unknown input in this form. In this presentation, we will look at numerical examples. So when we look at this decomposition, we can see that it is in the seamless form, where it involves only one output measurement. It involves the first derivative of one output measurement, and it contains a linear function of the stack vector x bar 1 of t, which is a reduced order disturbance-free system. What I like to have in here also is the MATLAB software. I also have the MATLAB software as well, and it will be used for the decomposition for the numerical examples. And I also have the codes for doing the decomposition. So let us take the following example 1, where we pick the matrices A, D, and C arbitrarily. Here we pick matrix A, which is a 4x4 matrix, and it's arbitrarily selected. And we also pick matrix D, and we make the elements in matrix D just simply 1, 2, 3, and 4. And likewise, we pick the matrix C to be a 2x4 matrix. So in this example, the system is a linear system with one unknown input, and we have 4 stack variables in the stack vector. We have 2 output measurements, y1 and y2. So p equal to 2. P is bigger than this unknown input. All right, so let's say that we want to do the decomposition, and let's do it by using the Hou and Muller decomposition method. Okay, according to Hou and Muller method, we require the observer matching condition to be satisfied, and it is. So this column is non-zero. So if we go ahead and implement the codings using Hou and Muller method, this is what we put in. We have the matrices A, D, and C. The first thing we need to do is we need to check the observer matching condition holds or not. Of course, this should give us a non-zero column. And according to Hou and Muller method, as we went through in previous presentations, the matrix P and matrix V is obtained as follows. We arbitrarily select matrix P because according to Hou and Muller, as long as matrix V is invertible, that's how we can pick matrix P. So here we just pick it arbitrarily to be 1 and 2, and then we check to see if it's invertible. So let's cut and paste this into MATLAB. And when we compile into MATLAB, we should see the following results. So we see matrix I, D, C is the enter, and we look at the column, we see the product of C and D is non-zero, and the matrix P here is arbitrarily selected. It happened to be 1 and 2. So we obtain this matrix V here. And we have to check to see if it's invertible. Of course, it's invertible according to the example. So what we do then is we obtain an inverse of matrix V, and then from there we extract matrix V1 and V2. The answer for here is 2. That means that the rank is full invertible, and we obtain this inverse of matrix V. And then we obtain V1 and we obtain V2. And then what we do is, according to Hou and Muller, we can select an arbitrary matrix E as long as it's full rank, and matrix T is invertible. So that's where the coding for that. And we can then check to see if it is invertible, and the answer is yes. So here we pick E arbitrarily, full column rank matrix. That's why rank there is 3, and then we construct the matrix T, and then we check the rank. It's all good. It's actually invertible. So that means that we can do the matrix transformation, and we can obtain the sub-matrices according to Hou and Muller method. We can obtain all these sub-matrices. Okay, so that's what these codes are for. Work out the inverse. And by the way, the inverse of the matrix T times D give us a special form. Give us a special form, and this is the special form there. It's actually 0 column matrix and 1. And that's the nature of the decomposition, which we discussed that in the topic talk 1. That is the special structure of the inverse of T times D, as long as matrix T is chosen according to this selection. Okay, right. So we done the decomposition. We done the inverse of matrix T. We obtain matrix A bar, and then we partition and we obtain all the sub-matrices. And so according to Hou and Muller, we would then be able to obtain an n-1 reduced order system with no unknown input, where in here we get a third order system with no unknown input. And that is from this structure here. Okay, so that is basically what we went through in the talk 1. So we obtain this reduced order matrix, and where this reduced order matrix is given by this formula, and so we do the coding accordingly. So we then say, all right, this is how we obtain the matrix I tilde 1. And it's basically A bar 1, 1, take away A bar 1, 2, times V1 CE. And then we also obtain the matrix A tilde 1, 2, where we denote it to be A bar 1, 2 times V1. And then we also obtain this output matrix C1 tilde, and it is equal to V2C. So if we execute this code, then we would be able to obtain an n-1 reduced order disturbance-free system. And we obtain those submatrices accordingly. Okay, so that's where we have them given in this form here. All right, so that's where we got matrix I tilde 1, I tilde 1, 2, C tilde 1, as well as we can obtain this output measurement vector in terms of the original output measurement vector, and its V2 is given as follow. Okay, so we have here V2 as well, which is that 7 and -3 in there. So that's where we got the reduced order disturbance-free system. And to get the disturbance in its entirety, we can also obtain it as well. By the way, we also check the observability condition of the pair I tilde 1 and C tilde 1. It is observable, which gives us a rank equal to 3. Then we proceed to obtain an expression for the unknown input. And if we go back to the description of the unknown input, according to Hou and Muller, it is given by this expression. So we need to work out what is the metric Q1, what is the metric Q2, and Q1 is given by this expression, similarly Q2. So we just implement the code there. And so we got the unknown input, dt is given by V1 and Q1 and Q2. So if I copy this bit into MATLAB, I would be able to obtain V1, Q1, and Q2. And that's what we obtain. So according to the results we got using Hou and Muller decomposition method, we obtain metric V1 to be minus 0.2 and 0.1, and metric Q1 and metric Q2. Now, what we like to discuss here is that according to this decomposition, metric V1 is basically contains two non-zero elements. The reason for that is because there was no guideline on how we pick metric P. So in this code here, I just pick it to be arbitrarily 1 and 2. And based on this selection, that leads us to this metric V1. And of course, according to this decomposition, clearly when we take V1, we multiply by y dot of t, we required the first derivative of measurement y1 of t and the first derivative of measurement y2 of t. All right. So that's how we obtain the decomposition of the unknown input, and as well as a reduced order disturbance-free system. Now, let us focus on our approach. In our approach, what happened in here is, under this assumption that it's a non-zero column matrix, we can see that there are two non-zero elements in this matrix. So what that means is we can have an option. We can actually can pick output measurement y1 of t in our decomposition in obtaining the disturbance, which is in term of y1 dot of t and y1 of t. Now, if we do that, then we will get the disturbance expressed in this form, where we got beta 1, y1 dot, and y1 in here. And so when we pick the first output, alpha 1 is 30. All right. So if we do the decomposition based on our approach, this is what we're going to have. So we got this coding here. So we have this coding based on our approach. Again, we just enter the matrices A, D, C, and we check to see if the observer condition satisfies these, where we got alpha 1 equal to 30. Now, according to our decomposition method, what we do is we pick, in here, we pick the metric P according to the following form. Okay, so that's where we pick the metric P. C1 is the first row of the output matrix. So we pick P to be this form. Then because you got only P equal to 2, so we pick it to be 0 and 1. It's important to note that it's a 0 in here. And so we obtain metric V based on this definition. And of course, it's an invertible matrix. So we obtain V1 and V2. So let me copy and paste these codes back into MATLAB. And let me clear up the whole thing, and let's paste them in there. We can see that the V metric here got this special structure. And as a result, when we take the inverse, we got V1 is in this form. So it has a special structure that we discussed about. Okay, it's got this special structure. This special structure. And so we got V1 and we got V2. And then after that, we're going to compute metric E. Now remember, we say that metric E is the null space, orthogonal of the null space of the row V1C. So this is the command for evaluating metric E. It's null of V1C. And it's if I cut and paste this one in, I will be able to obtain metric E. There you go. That's metric E. And we can then, we can always guarantee that it is full rank. That's for sure. But this one just to show you that this is a full rank matrix. There you go. So we got a metric T, which is E and D. There's metric T. And if I take the inverse of it, it should exist. And then we should be able to do the decomposition, and we should be able to obtain all the sub-matrices. We can obtain all the sub-matrices. So we obtain the sub-matrix A bar 1, 1, A bar 1, 2, A bar 2, 1, and A bar 2, 2. And then we would be able to obtain the rest of the decomposition, which is dt equal to beta y1 dot plus gamma 1 y1 and the linear function of the stack vector. So let me cut and paste all of that code into MATLAB, and we should be able to get the decomposition done very, very easily. And so this is the results of the decomposition. Okay, so we do our approach, and we pick y1, and therefore we have the decomposition in this form, and as a result we get beta 1, gamma 1, this linear function of the stack vector x1 bar of t, and we obtain submatrices for the reduced order system. Okay, and keep in mind that this reduced order system contain in here the output measurement y1 of t. And by the way, the pair of the reduced order system pair, this pair here is also observable. Likewise, in Hou and Muller method, that pair is also observable. All right. Now, on the other hand, we also have another option. And the other option is we could pick y2 and select the first derivative of y2 of t in our decomposition. So we can express the unknown input dt in terms of y2 dot of t. So that is another flexibility in our approach. The reason why we can do it is because when we look at the output matrix C2 associated with output measurement y2 of t, when we multiply by d, it's in fact a non-zero element, which is what we found from here. So if we pick, instead of y1 of t, if we pick y2 of t, and use it in our decomposition for the unknown input, which is this form here, it can be done. It's no problem at all. And what we do is we're going to rearrange the output measurement vector, and we're going to put the second output into the first entry in here, and then we swap, basically we swap the order of the output. And therefore, we got a new matrix C, which is C2 and C1, which is this new matrix here, where we swap the row. It was row number 2, now it become row number 1. And then we follow exactly the same process, exactly the same analysis, which is basically according to the algorithm or the summary that we went through in our previous presentation. Okay, so we do that. Here is basically the codes for the decomposition using y2 of t. Now, when we look at the way we did it here is we just simply rearrange the matrix C. We make second row become first row, and first row becomes second row. And then we select the P matrix according to that special structure, and then we obtain submatrices V1, V2, and then we obtain the matrix E by taking the null space of V1C, and then the rest of the decomposition can be done. All right, so what we can do here, we just cut and paste that into MATLAB, and we clear it, and then we obtain these submatrices for the decomposition, where we can express the unknown input in this form. Keep in mind that it is now in terms of the second output measurement. All right, so we got beta 2, gamma 2, and all of that accordingly. So we have here beta 2 is 1/70, which is alpha 2. Alpha 2 is 70, so 1/70. And then we have gamma 2, and then we got this I bar 2, 1, which is a linear combination of the reducer, the disturbance-free system. So the unknown input is in its simplest form, and the reduced order system, disturbance-free system, contains the output measurement Y2. Of course, the output measurement Y bar of t is a function of V2 Y of t, and we also obtain V2 in here. So that's how we got the decomposition. Have a look at I bar 1, 1. There you go. And I tilde 1, 2. By the way, I tilde 1, 2 is basically a single column because V1 has a special structure, and so we just pick the first element of it, and that's where we get this I tilde 1, 2, which is the one in here. All right, and what else? We also obtain the matrix C tilde 1, which is V2CE, and this is given us below. And also, by the way, the pair is also observable. So as you can see from numerical example 1, given this system, we have two ways of expressing or decomposing the unknown input, because the product CD gives us two non-zero elements. That means that either the first output measurement or the second output measurement, they can be used in the decomposition. If we pick the first output measurement, then the unknown input is expressed in this form. It contains the output measurement Y1 of t. And the reducer system is in terms of Y1 of t. If we use the second output measurement Y2 of t, this can be done because that still gives us a non-zero value. So we can then rearrange the output vector, and then we can proceed with the normal process. We obtain the disturbance expressed in terms of output measurement Y2 of t. And then the reducer, the disturbance-free system, contains the output measurement Y2 of t. And Y bar of t is a combination of Y2 of t and Y1 of t. So that's how we do the first numerical example. In the second example, we're going to pick another matrix I, D, and C, where we pick a higher order system, and we pick it to be a sixth order system where n equal to 6. So we've got 6 stacked variables. We're going to pick 3 output measurements, and bear in mind that this output measurement is actually in the canonical form. So what happened in here is the first output contain first variable x1, second output is second variable x2, and the third output is the third variable x3. We just pick the unknown input metric to be 1, 2, 0, 0, 1, 0. It's a column. And this is just the notation that this is the transpose of metric of this row here. Okay. So we have n equal to 6. We got p equal to 3. And we have 3 output measurement. So the first thing we do is we check to see if this condition holds or not. And the answer is yes. So that means that the observer matching condition actually holds. And we got the product, which is C times D is a column, and it's contain 2 non-zero elements. So that means that we have C1D equal to alpha 1 with C1, and C2D is 2 with C alpha 2 equal to 2. So we have an option of selecting either y1 of t in the decomposition or y2 of t in the decomposition. And we're going to look at both of them all together. Okay, so let's have a look at the coding for the second example. So in the second example, the coding is very straightforward. We enter metric A, D, C, and we check to see if it is observer condition is satisfied or not. And then we select the P matrix according to a special structure. And then we obtain the metric V. We do the inverse. And because in here, metric C is in canonical form, and we pick the first output measurement. So we select metric E to be in this form. And of course, when you look at it, metric T is invertible. So we follow in the process, we pick metric P, and then we obtain metric V, and then we work out the inverse of V, and we get V1. Have a look at V1. It's actually of a special structure. It has only one single non-zero element that corresponds to the first derivative of the output measurement, y1 of t. And then when we look at this row matrix, and so the orthogonal basis for the null space is just simply this expression. All right. And then as a result, we can easily express the unknown input in terms of the output measurement y1 of t. And then the rest of the reduced order system can be obtained. And this reduced order system is in terms of the output measurement y1 of t. So if I just cut and paste this example where we enter all the commands, we enter the matrix P, V, T, and then we do the decomposition, and then we obtain the rest of the submatrices. And so we obtain the reduced order system. Okay, and because alpha 1 is 1, so this matrix here is in fact the submatrix A bar 1, 2. So A bar 1, 2 is the same as I tilde 1, 2. And the output matrix for the reduced order system, C tilde 1, is again in the canonical form, but of a reduced dimension. So we got the decomposition, and it is in a very seamless form, Now, on the other hand, if we say that, okay, because we got two non-zero elements, and let's say for some practical reason, we need to use the first derivative of the second measurement, then that means that we're going to pick it. And in the decomposition, we can express it in this form. And we then obtain a reduced order system of dimension n minus 1, which is a fifth order system, and it's in terms of the second output measurement. Have a look at this. This is derivative of the second output measurement. And so the way to do that is very straightforward. This one is non-zero, it's equal to 2, so alpha 2 is 2. We rearrange the output measurement. We make the second output to be the first one, and the rest of them, we have y1 and y3. So this new C matrix is that this first row corresponds to second output measurement. And so if that's the case, that CD will be 2, 1, 0, and we select the metric P again in this special structure, 0 and identity. And because it's in this form, we can easily take the inverse, and we obtain metric V1 in this simplest form. It has one non-zero element. And likewise, we can obtain metric V2. And we can pick the metric E, which is the null space of V1C, and it has this very simplified form. You see that the second row here is 0. Because when we got V1 times C, C is in this particular term here, we need to make it 0 there. So either ways, this can be easily obtained, and it is invertible, and so we obtain the unknown input expressed in its simplest form in terms of the second output measurement, and the rest of the parameters or the submatrices, they can be easily obtained. And bear in mind that the output vector in here is actually of this order. All right, so it's actually have y2 in this first entry. And so that is the codings based on output measurement y2. There, this is based on output measurement y2. We rearrange the output matrix, and then we continue with the rest of the code similar, the same as the previous one. And we obtain all the submatrices. So let's say we got I bar 1, 1. I bar 1, 1 is given by that one, 10 minus 1, and so on. Okay. So as you can see, the way to obtain the decomposition is very easy. It can be implemented by simple codes in MATLAB, and we can easily express the unknown input in terms of whichever output measurement that we like it to be in terms of practicality of it. And of course, it is required that whichever output we pick, it has to satisfy the matching condition. In other words, the matrix C I times D has to be non-zero if we select yi of t to be used or to explicitly express it in terms of the unknown input. Okay, so we we went through a number of numerical examples, and we show how it can be easily done. And so in the next presentation, we will look at part 3 of topic 2, where we will design an unknown input observer. And the way we design a unknown input observer is we're going to use a functional observer to estimate the function z of t, which is the linear combination of the stack vector x bar 1 of t. And with this representation, with this form, it is the simplest unknown input observer that use the minimum order linear functional observer, and it use only one output measurement and its first derivative. Okay, so thank you everyone for watching, and I hope to see you again in the next video. Thank you and bye for now.